Okay, welcome back. We're going to start today with time dilation, which remember there's three things that are affected. There's time dilation, there's length contraction, and there's mass increase, which is also can be interpreted as momentum, relativistic momentum. Now, for time dilation, let us think about the concept of. So the best way to understand time dilation is through the concept of a clock. Now, I've got this statement written down. I'm saying moving clocks run slow. So let's first of all, let's kind of explain the theory, and then we'll go into the mathematics to describe how it works. First of all, what we want to see here is we want to see, let's say, the Earth and a person standing on the Earth. I know that's a big person. And then we want to have a spaceship, and the spaceship is traveling at, some large quantity or percentage of the speed of light. And there's a person inside the spaceship as well. Now, when the person inside the spaceship measures something in their own reference frame, like an event, this is known as T naught. Now T naught is time as measured from the same reference frame. So you see here I've added this sentence, time as measured from the same reference frame. Therefore, there is no relative velocity between the observer and the measured event. That's T naught. So now let's be clear about this. If the person on Earth is measuring something on Earth in their own reference frame, it would be T naught. If the person on the spaceship was measuring something inside their spaceship, they would, like a time that would take a certain amount, like a clock or an event that took some time, then that's called T naught. However, if you measure something that is relative to your own reference frame, then you're measuring T. So that is the time of an event as measured in a different inertial reference frame than your own. So to be clear here, I just said time as measured in a different frame of reference than the observer. In other words, there is relative motion between the event that is being measured and the observer who is doing the measuring. So, for example, if we go back to our picture up here, I could say that, hey, the person on the Earth, again, let's take the person on the Earth, if they were measuring an event inside the spaceship, then that would be T, not T naught. Alternatively, if we flip this scenario around and we ask the person inside the spaceship, hey, can you measure something that's happening on Earth? Again, this would be T. Why? Because it's a mirror effect for each person. In other words, the people in different frames of reference are going to observe the same thing of each other. So the person on Earth will say that the clocks on the spaceship are running slowly, and the person on the spaceship will say that the clocks on Earth are running slowly. Why? Well, because there's relative motion between them. We don't say that the spaceship is moving. After all, you could say that the spaceship is not moving and that the Earth is zooming by at 0.8c. Remember, we talked about this before. There's no difference in those two scenarios. All right, there's an equation that describes time dilation. And this equation, I'm going to write it down, and then we'll kind of go through and try and figure out how it came about. But it says T is equal to T naught divided by the square root of 1 minus v squared over c squared. Now, so this is the time dilation equation. Question is, how does this, first of all, let's state a relationship, and that is that dilated time is greater than time measured at rest. Now v is the velocity that obviously is less than the speed of light, but how does this equation come to be? Or how does this equation derived? How do we figure it out? The easiest way to do this, we'll come back and we'll kind of talk about how to use it, but first let's try and figure out how it was derived. The best way to do this is to simulate a clock. How would you create a clock? Well, one way to create a clock is to, there's like quartz clocks and different types of Swiss clocks. But one way to make a clock is if you have a pulse of light, like a laser, that starts on one side of a distance, L, and the laser travels this distance, L, and it hits a mirror, and it's reflected back. So it goes there, and then it comes back. Okay? So now let's ask ourselves, well, how can we use this as some kind of a clock? I mean, all we're trying to do is measure a certain time interval for a clock. So let's go back to our original equation for constant velocity, because light is traveling at a constant velocity. And our equation is d equals v times t. Now we know that the distance in this case is, now you might be tempted to say that the distance is L, but in fact you'd be wrong, because remember, the light traveled to the mirror and back again. That means the distance is 2 times L. Okay? And the velocity, well, this is a laser beam. So the velocity is the speed of light. And the t, well, that's t naught, because we're measuring something in our own reference frame. Okay? So it travels this distance 2 times L, and then that's the velocity is c, and the time it took is the time in our own reference frame, so it's t naught. Okay, great. So far, so good. Now what we're going to do is, this clock was observed in our own reference frame. Now we're going to observe the same clock, but now from a relative reference frame. Now, before I do this, I actually want to kind of show you a different analogy to be able to understand these directions. So give me a second here. And if I have a swimming pool, and in this swimming pool I put a boat that is aimed like this, and the boat travels in this direction, then this boat will travel straight across the swimming pool. Now think, instead of having a swimming pool, I have a river. And the river is the water in this river. Oops. The river has water flowing in it, and this water is flowing to the right. Now, if I put my boat in the same location and have the boat head in this downwards on the direction, then the boat actually doesn't travel in that direction. The boat, a time later, the boat will end up here. And then a certain time even later, the boat will end up here. So the boat's actually traveling on a diagonal. Even though the boat is propelling itself in the same direction as it was in the swimming pool, because the water has a velocity, the boat ends up traveling in a diagonal line. Okay? So, now that you accept that, let's go back and take a look at the light. It's the same situation. So now let's do the same thing with light. It's the same clock. It's just that now, when the clock puts out a pulse of light, when we view it from let's say from Earth, then we're not going to see the light go up and down because the clock is in a spaceship. This whole clock, remember, is now inside the spaceship. So as the light leaves the laser beam, it doesn't travel straight down, it's traveling on a diagonal. And now it hits the mirror, and then it travels back up on a and then it finally gets to this place here. Now, the vertical distance here is still L. Okay? But now we have, in this situation, I can maybe draw in a different color, I essentially have a right angle triangle. Okay? Can you see this? There's this, I know that's that looks like a sinusoid there. Let me see if I can do that again. Okay, straight line, straight line, straight, I give up. Okay, straight line. Anyways, if this is a right angle triangle, then we should be able to use Pythagoras to solve it. Let's figure out how we do that. Okay, we know one side is L. Okay, so like if I draw a right angle triangle, right? Okay, so like let's just use math for a second. Okay? If I say ABC, then we know from Pythagoras, I know a squared plus b squared, is equal to c squared, right? That's Pythagoras. Now, how do we relate that to these distances here? Well, let's erase this for a second. We don't have ABC. What we have is L. Okay, that's L squared. That's the vertical side here. Now, what's this side? Okay, guess what? The distance that it's traveling sideways, well, that's related to the velocity of the ship, correct? Remember, what's distance? Distance is equal to velocity times time. But remember what the time is. The time is the time from here to here. That means this distance is half of that. Okay? That means the distance that we're dealing with here is v times t divided by 2. Okay? So now, if let's also do the hypotenuse here. Okay? By the way, this t, notice I did not put a naught at it. Why not? Because, excuse the pun, why not? Because this t is measured by the person on Earth. Therefore, this is time dilated t. Okay? Now, the question is, what about this distance here along the hypotenuse from here to here? Well, that's the path of the light. And the distance that the light travels is, again, but now it's not c anymore, it's not v anymore, it's c. So it's ct, but wait a minute, this time, again, it's the time from here to here, from here to here. Now we only want the distance from here to here. That's half of that, isn't it? So therefore it's ct divided by 2. So now we have all three sides. This side here is vt divided by 2. This side is ct divided by 2. and this side is L. So let's just erase this for a minute, and let's start again. Let's do it here. We're actually trying to write out Pythagoras' equation. Okay? Here it is. It's like remember a squared plus b squared equals c squared? L squared plus vt divided by 2 squared is equal to ct divided by 2 squared. Okay? Now, wait a minute. There's no t naught in this equation. So what I'm going to do is I'm going to come back up to here, and I'm going to solve for L. And I'm going to say L is equal to c times t naught divided by 2. And now I'm going to substitute this value, this equation in for this L here. So now I'm going to say c times t naught divided by 2, and then I'm going to square that. And now I'll just write the rest of the equation. And now I'm going to basically just do a little bit of algebra with some math to make life a little easier for myself. Let's see what we get. So let's square everything, and at the same time, notice the denominators are all going to be 4. So I'm just going to get rid of those 4's. So I'll have c squared t naught squared plus v squared t squared equals c squared t squared. Okay? Now obviously I have the I can put it in. I have them divided by 4, 2 squareds, but they all cancel out. Okay? Now what I want to do is I want to collect t terms. Notice this is a t term and this is a t term. I want those to be on one side. So I'm going to put those both on the right-hand side. So let me write it again. C squared t naught squared equals c squared t squared. And now I'll minus the v squared t squared. Minus v squared t squared. Okay? And now what I can do is I'll factor the t squared out. Notice these two t squareds are in both terms, so I'll go c squared minus v squared multiplied by t squared. Okay, and the left-hand side stays the same. Okay, so far so good. Now what am I trying to do here? Well, I want an equation where I have t equals something. So I want this guy by itself. I want this term by itself. So I'm going to divide the right-hand side by c squared minus v squared and the left-hand side as well. So I'll have this on the left. And now on the right, if I divide by c squared minus v squared, it cancels out and I'm left with t squared. Okay? Now what I can do in order to simplify even further is this left-hand side of the equation, I'm going to divide the numerator and the denominator by c squared. Okay? So now I'll get like this. So divide the top by c squared, and I get c squared t naught squared divided by c squared. That's the top. That's the numerator. Divided by, now I'll divide everything in the numerator by c squared minus v squared divided by c squared. And that's all equal, still equal to t squared. Now notice this guy cancels out. This guy cancels out. This guy gives me a 1. So what do I end up with? In the numerator, on the top, I have t naught squared divided by 1, which is c squared divided by c squared, minus v squared divided by c squared. And that's all equal to t squared. Now I'm going to take the square root of both sides. And so, if I take the square root of the right-hand side and the left-hand side, I get t naught. Take the square root of that, and you're just left with t naught, right? square, take the square root, and then you take the square root of the denominator, and that's equal to t. And there is my equation for time dilation. That's the first equation I wrote, and that's the derivation of it. Now, I'm not going to ask you to be able to derive it, but I am going to ask you to be able to memorize that equation. So here's a question I want you to try and answer. An astronaut brushes his teeth for 1.5 minutes as measured by the astronaut himself. And the question is, how long did he brush his teeth according to someone on Earth if the spaceship was traveling at 0.6 c speed of light past the Earth? Pause the video now and see if you can figure out the answer using the time dilation equation provided. Okay, let's solve this problem now. What I like to do is I like to write down the values that I am given. So, for example, the initial value that I'm given is the 1.5 minutes. So now I know that's T naught is 1.5 minutes. Okay? And also, I know that the spaceship is traveling at a velocity of 0.6 c. So now if I use my equation, t, and what, oh, by the way, what am I trying to find? I'm trying to find, according to someone on the Earth, it's in a relative frame of reference as to how long it takes to brush the teeth. So I'm actually trying to find t here. So I say t equals t naught divided by the square root of 1 minus v squared over c squared. And so therefore, I end up with 1.5 minutes in the numerator divided by the square root of 1 minus 0.6 c all squared divided by c squared. And so now I end up with 1.5 divided by the square root of 1 minus, and the c squareds cancel out, and I'm left with 0.6 squared. And now if I get my calculator, that's going to give me, so that gives me 1.875 minutes, or if I multiply that by 60, I'm going to get 112.5 seconds, or if I wanted to round it to 3 sig figs, 113 seconds. Okay? Let's try another problem. So the question is, a space station passing Earth at 0.86 c cooks a turkey. A person on Earth notes that it took 4 hours to cook the turkey in the space station. So this is a different frame of reference. How long does the chef in the space station who is actually doing the cooking say that it took to cook the turkey? Pause the video now and see if you can get the answer. We are given that the velocity is equal to 0.86 c. We are also given that the time, now the question is 4 hours. Who recorded this time? It's a person on Earth. And what are they recording? An event that takes place in the space station. So they are recording an event which takes place in a different frame of reference. Therefore, the time that we have measured of 4 hours is in fact t, not t naught. Now we're asking the chef who is in the space station where the turkey is actually being cooked. What time is that? And that's t naught. Therefore, when we write the equation out, we have this, but we're not looking to solve for t, we're looking to solve this term. So we have to do a little bit of algebra to rearrange it. So we can say, no problem, we can say t times the square root of 1 minus v squared divided by c squared equals t naught. And now we can plug our values in. This is 4 hours times the square root of 1 minus, and we've got 0.86 c squared divided by c squared. So that's just going to be 4 times the square root of 1 minus 0.86 squared, because the c squareds will cancel out. And for the time, we get 2.04 hours. And that's the end of that problem.